Hey guys, what's up? Eddie Aho here with KISSanalog.com. Today I want to come to you with another KISS University video using MicroCap. And what I want to do is look at RC time constants, how you make filters out of them, and how you can simulate it and make that, design part a lot easier using simulation. And then when you come to the lab, you're pretty sure it's going to work, okay? And I want to talk about some circuits that you might want to use it in and give you some examples and just go over a brief summary of the RC time constant. Let's do it. Oh, here, let me start with this board. Alright, so I've just drawn a simple circuit here. Voltage source, a switch, resistor, capacitor. And this might be where the circuit comes, connects into this little thing here. And so we're going to filter what comes into this part of the circuit, okay? So let's just go over some basic, circuit analysis, all right? Just kind of make it simple. When you first close that switch, this capacitor doesn't have any voltage on it, so it looks like it's short. Capacitors look like short, during fast transients and are relatively, fast transients compared to the size of the capacitor. So as soon as you close that switch, this capacitor is going to charge up. Now when you get to the DC analysis, that's a transient analysis. When you get the DC analysis portion of it, that's after everything's settled down. After everything's settled down, this guy's charged up. He's charged up to what? Same as this voltage, right? No more current's flowing, so there's no current flow, so it's almost like an open circuit. This voltage will equal to this voltage. There's that Kirchhoff's voltage law that all voltages around a loop will equal 0. So you have a plus voltage here, but if current's flowing this way, you'll have plus sign here, and so this voltage drop will cancel with that one. Then current comes this way, you get plus minus. So these two guys are in series. The voltage drops on these two, add up, subtract to that, you end up at 0. During the transient analysis portion of it, there is current flowing, so you get voltage drop, voltage drop. When you get to the DC analysis, well, current's no longer flowing, unless this is a real leaky capacitor. Then you might have microamps, that kind of thing. But, practically there's no current flowing, so there's no voltage drop here. So all the voltage is here. So that's just want to cover the basic, analysis between the transient and the DC, what's happening in the circuit. Okay. Now what we want to do is kind of talk about how you describe what the voltage looks like here. Well, yeah, during the initial thing, it looks like it's short, but the voltage does grow on this. And what does that look like? So let's talk about that now. All right, I'm back. So what I've drawn here is I shrunk the circuit down, and I'm saying the voltage out off the capacitor is voltage C, VC, and I got this graph here. So this is the voltage VC as it charges up the capacitor, and yeah, I got my voltage resistor, put a ground symbol here, and I got rid of the switch because in MicroCap what we're going to do is we're going to put a pulse. We're just going to pulse the wave just so it'll look just like a switch closing, right? That's the easy way to do it because yeah, so we'll show you that in MicroCap. Now here's the equation for charging a capacitor, for the voltage charging up. When you do the math on this stuff to derive this formula, you go through some calculus, you integrate, because this capacitor is basically an integrator. It's going to charge up and use the calculus to finally solve for the algebraic term, and you end up with this kind of a logarithmic term here, this exponential term, and whenever you have that, you're going to have something shaped this way. Okay, so that's the equation. Now the interesting thing about this equation, this e to the minus t over RC, sometimes you see that RC is shown as a tau, like that funny looking T, but I just wrote RC in here. One thing I want to say about this is this term right here. So the VC is equal to this voltage times this stuff. So it's voltage times 1, so it's that voltage, whatever this voltage is, minus this thing is what this guy looks like. Because as this guy charges up, you're going to subtract that from the voltage, and anyway, you end up with this term here, right? So now if you wanted to plot the current that's going to the capacitor, it'd be just the opposite. It'd be just this term. It'd be current times e to the minus t, or you get rid of the 1 minus part. You just multiply your current by the e minus t over RC. So it would look just like, you know, the flipped over version of that. Now on the other hand, let's say that you turn off, once you charge up, then this voltage turns off and it shorts itself, so the capacitor drains itself back out. Well, then the voltage would discharge the same way. It would look like that current charging. It would drop this way. What I also showed is this equation here is I equals C times dV over dt. Sometimes you see the delta symbol. Oh, this is the lowercase delta symbol, the D, instead of the uppercase triangle symbol for the delta. So that, what that means is change of voltage. So let's say the, I don't know, let's say this is a 10 volt signal, okay? Well, then the voltage is going to change 10 volts. So that'd be a change of 10 volts, and over the change of time, whatever that is, you'd put that here, and then the capacitor is 1 nanofarad. And now the thing is, you don't really know what the dt is. If you're gonna solve for dt to see how long it takes for that to happen, then you solve this equation. So the dt is over here and I is under here. So it'd be dt is equal to c over c times dv divided by I, and I would be the current charging to the capacitor, which would be the voltage divided by the resistor. Okay, so this is an approximation formula. It works for straight lines. Okay, a lot of times in power electronics we're using this formula. Sometimes we're using this one, and it just depends. I just want to show both to see the difference. Now you can see how fast this rises. That's almost like a straight line there. So between here and here, you could approximate that using this formula to get here, and then you could approximate portions of this. Or you could just approximate the major portion. You can see what I've got here. Let me explain this. I got T1 here. I meant to put T2, T3, T4, and T5. Okay, the first 5 time constants. And what a time constant is, it's just the RC value. RC is the constant because it's the constant in your circuit. And so whatever R times C is, that's your time constant. And when the time is equal to RC, this part right here becomes -1. And when it's here, it's -2. This whole thing becomes -2 up to -5, right? So if you put that in your calculator, go e to -1, -2, you'll get these numbers. It'll be 63%. So the capacitor and the first time constant, if RC is equal to say 1 nanosecond, in 1 nanosecond it'll be 63% of say 10 volts, if that's what it was. And second time constant, 86%. And then you can see how they get crunched, 95, 98, 99. So it flattens out after about the second time constant. So really, the first 2 time constants, you're getting pretty charged up. And then that means also the current going to this part is a lot less than it was through this first part. Now, one interesting thing to think about is when you look at rise times of signals, usually you zoom in. Let's say you zoomed in the rise time of a square wave and you're reading the rise time. It's not going to quite look hopefully that bad, right? But if you zoom in to that edge, usually you start at 10% above 0 and you read the time up to 10% of the top, because those 2 things can really kind of skew the actual straight line. Like your rise time might be like this, and then it's skewed because it takes forever to get that last 10%. And you can kind of see why, because if you think about that, take off 10% here, 10% up here, that's 80% left over. So 80% of your wave shape is really what you're using for rise time. Well, if you think about that, you know, 86%, your 2 time constants, you're beyond that. So really, your rise time is within the first 2 time constants if you think about it like that. Okay? I mean, it kind of makes sense to kind of correlate these things together. All right, so now I want to show you an example of a circuit that this exact thing would be used in, and it's used in just about every single power supply there is. Okay, let's look at that. Hey, and just before we go look at that thing, what I want to kind of go back to is, let's say that square wave. This was a square wave, and we are going to put a pulse over here. Well, if you had some noise on the front end of that square wave and you just wanted to filter that, you see how you could do that? All you have to do is smooth it off. Okay? There's a clue for what we're going to get to in the next board. Alright, I'm back with my example. I've got a portion of a power supply drawn up. This could be a Ford converter, for instance. Or, you've seen a lot of the converters where there's a magnetic inductor transformer tied to a MOSFET that's switching on and off. And this is the voltage of the drain. And that, when this guy turns on, he's pulling current to this magnetic, this inductor transformer. And then it goes to this sense resistor. Usually a small value, so you're not burning any power up, or, and plus you don't want too much voltage drop here at the gate to source of this guy, right? So you pick up off this point right here, and you do this RC filter back to your current sense input. And this chip, this control IC that's controlling the FET, if it's in a current mode control, he's looking for the peak value. Let's say this peak value, this triangle, before he says, okay, once that hits maybe what it equates to 1 volt, it'll say, okay, turn off the FET. So then the voltage on the drain bounces back up, it's off. So it starts off here, the FET turns on, pulls down. When it pulls down, it pulls current through. And then when this thing rises to a certain value, he turns it off, boom. And then that's how a pulse width controls the duty cycle of this FET. Now what happens is, and this is going to be triangular shaped because remember, current in an inductor is a choke. Transformer is a choke, right? It's another word for it. It chokes off the current. It doesn't like current changing instantly. Just like a capacitor doesn't like voltage changing instantly. Voltage has to charge up on a capacitor, but current can change instantly through a capacitor practically. It's just the inverse for an inductor. The voltage can flip. You get that kickback voltage, right? On solenoids, magnetics, you can get a kickback voltage that can be very high voltage. But the current wants to not stop or change or start instantly. So it rises, it ramps up. And what happens is when this FET turns on, it creates a spike. And that spike, there's a voltage spike, and you don't want this feedback, because basically on a current mode control, which a lot of power supplies are driven off of, when it looks at that, it's going to see that as like, oh, there's my trip point. I just barely turned on. Okay, I'll turn right off again. And you don't want that to happen. So you set up this RC filter, this resistor and this capacitor, to smooth off that first transition. Let's say this is running at 100 kilohertz or something, and you've got microseconds of on time at least. Maybe at least a microsecond, let's say. Well, then you say, well, okay, 10% of that, 100 nanoseconds. I could put a filter for 100 nanoseconds so that that first couple rise time constants smooths off this, basically kills it, and then that way it doesn't trip my thing. And then time goes on, it charges up, and then it finally hits the trip limit and it trips where it's supposed to. So basically you don't really care about what's happening here, but you don't want to have that time constant too long because you don't want to take too much of this time in this, because that'll limit how narrow that pulse width can get before the filter starts to kind of give a fake feedback, because the feedback signal it's letting in is lower than what it should be. Let's say it's, you know, in the first time constant. If your first time constant gets into the point where you want to start limiting your duty cycle, say you've made a time constant of 300 nanoseconds. Well, if your duty cycle starts closing in, trying to control the voltage, you know, your feedback, if it's trying to control what's going on out here, and the duty cycle is limiting itself down to 200 or 300 nanoseconds, and then you're inside that filter, now the filter is actually not giving the proper voltage feedback. So yeah, you got to think about those things, and MicroCap can help you. And so let's go look at MicroCap. This is just one example, a practical example of how that filter can be used. So let's look at MicroCap. It's going to be a pretty quick tutorial on the MicroCap. All right, and there's a gotcha in MicroCap that if you're not paying attention to, it's a gotcha. So we'll point that out. All right, guys, let's start MicroCap 64-bit. Okay, and tip of the day comes up. I leave these on just as reminders of things I do know and things I don't know. Okay, I'm going to size this window, come over here where the magnifying glasses are up here, and I'm going to click on this guy. All right, so then it maximizes this schematic to fill the screen. I could pull this down a little bit and hit that again, and it'll just keep on zooming in till it fills the border. All right, so let's look at the circuit real quick. What we're going to do is we're going to do two RC time constants at the same time. That way we can compare two different time constants. Now, if you look close, this turns out to be the same circuit right now. This shows an exponential term, 1e2, that's the same as 100. And this one shows 1e9 minus 9, which is, 1 nanofarad. And down here, it's 1,000 picofarad. So same thing, right? Now I can change that by clicking here, or I could change it by adding clicking the capacitor symbol, coming up here. I can just change the C2 like this. So yeah, you can just change things how you want. Now, I can turn on the node numbers so we can look at all the node numbers. Let's do that. And then I can move these around if I want. Okay, I'm going to turn it back off. And if I hover over the node, it'll say node 2. And that's output 2. See that? Node 3, output 1. And node 1, and that's the in. It's just called in. And then right here, you notice how it highlights down here too, and if I touch here, highlights up there because they're the same node. They're both node 0. They're both tied to the ground symbol. Then I have this pulse symbol, which is different than what we've seen before. I'll open that just so you can look at it. You have these windows you fill in. It says in 100 nanoseconds, we're going to start to rise. And then P2 is 110 nanoseconds. It's the time delay to one level. And one level is this one. V1 is 4.6 volts. It says V1 is one level. Okay, and then if we continue P3, 1,000 nanoseconds to the trailing edge. That's where it's going to fall. And then P4 is 1,010 nanoseconds to 0, or 0 level. And if I come down here, it says 0 level. And that's 300 millivolts. Okay, so that's how you set up this. And then you also have these over here you can click on if you want and change things that way. So, just different ways to set up the generator. These are specific generators. Now, I'll show you where you find that. You come to components right up here, come down to primitives, then come over here and come down to waveform sources. Look at this. Here's battery. There's the voltage source, current source. And look, if you look down the bottom left corner, as I scroll over these, you see how it shows symbols. Come down here, there's the pulse. I just keep on coming down. Look, 3-phase, if you have that, staircase, noise,
there's NTC video stuff. So, and there's a user source. So really cool. This is, all kinds of different generators. And so that's where this one came from, that pulse generator right there. Okay. Now, normally I'd come up here and click on this guy and say I want that orientation right there. And then I'd click him here. And right here, this guy right here says the value is all this stuff. And then up here, I could turn that on if I want. And that stuff all comes from these windows here. And it's the same kind of setup, it's just a different way to do it. And as you hover over each one, it tells you what it is. Okay, so now I'm just to say okay, just so you can see how it places that thing. Now look, I can place another generator, say come up here, hit the arrow. Okay, now I have to click somewhere away from that, so unhighlight them, and then I can click just this guy and drag it where I want. Okay, so anyway, I can place this where I want, and I'm just going to drop it right here, because I'm going to go up here and undo and get rid of all this. Just wanted to show you different ways to do the same kind of thing. Now, let's come up here to analysis, probe transient down here. This is where we can kind of freehand probe. Hit that, and look, I got my voltage symbol selected right now. The probe is right there, it's selected automatically, so I come right here and hit VN, and there it is. Now now that I'm in this window, it's highlighted, I could come up and maximize that window if I want. Okay, now what I can do is I can come over here and hit this zoom, and I can zoom in on just one way just to see if it looks like what it's supposed to look like. And it looks like it. If I hold the mouse, that's about 100 nanoseconds it started rising, and about 110 nanoseconds, I guess, it reached the top, and then about 1,000 nanoseconds started to fall, and 1,010 nanoseconds it did. And it's about 300 and some, about 300 millivolts right there. It's not quite zero, right? I'd also come and grab this arrow thing, and let's say I click on right here and come here to there. That's whoops, you know what? I gotta get over to the zero timeline, right? So let's back up. Okay, now I'm at the zero. Let's zoom in again so I capture the zero over here. So I come out, okay, I come here and I go all the way to the edge so I get the zero. Okay, there's the zero right about there, I guess. Now if I come up and grab these arrows, okay, if I grab right closest line, and that's about 100 nanoseconds right there. If I come up here to this corner, that looks like about 110. And if I come over here, that looks like about a microsecond. Oh, look, I lost my decimal places. Now, if I go right to the bottom here, and if I let go of my mouse button, watch. Okay, yeah, so it shows me 110 nanoseconds about, So, yeah, it looks like it did what it was supposed to. Okay, I'm just going to go back up out of here. Actually, I'm going to go look at both windows. And let's look at the output. So let's come up here, size our window right there, and come to V2 out. Yep, there we go. Now, if this guy is the same time constant, if it really is, it should lay right on top of that red waveform. Let's try it. And it does. The green lays right on top. Okay, I'm going to come up to my arrow. I'm going to change this to 150, I think. And as I let go, it automatically does it. And look how it changed it. So if you wanted to filter something on this rising edge, you could do that. And I can say, well, maybe I don't need to filter that much. Maybe just barely. So put it 50. So see this green? It's just taken off that corner. But now look, you got to look at the bottom edge and see how it's also filtering the bottom. So you got to remember that. It's going to take a little while to settle. So you want to make sure your filtering's over before something happens over here if you're interested in that. All right, so that's how you can change your times and all that. Now this is also using the probe. I want to show you how to use this other transient window. Well, just before we do that, let's go back to probe transient, and let's go ahead and probe the output. I want to show you one more thing I've kind of forgot. Let's go to up here, probe, and then limits. And here's where you set the 10 microseconds. See, it ran to 10 microseconds. That's where you set that up. And it starts at 0. And maximum time step is that. Temperature is that. Okay? So that's where you can set the limit. So if it didn't set it up the way you wanted to after you ran probe, then come up here and do that. Okay, now let's go back to this and let's go to transient here. Now, when I run that transient, it comes up with this limits window. And here's the limits right here, but it also comes up with all this other stuff. And so down here at the bottom, you set up what you want to see. So X expression is T for time. And over here, Y is V for voltage at the input, voltage at output 2, and voltage at output 1. Then over here, X range, that's from 0 to 10 microseconds, and that's the steps right there. And the vertical range is 0 to 5 with 1 volt steps. And then over here in this column, I've got a tune of 2, so I'm only going to see output 2 and output 1. So I could put this input on frame 2 as well, or I could put it on frame 1. Let's just do that for fun. I'll run it. So see, inputs up here, outputs here. So this window 1, this window 2. Now I can come back up here to transient and say, now let's change that. I want to put them right on top of each other so I can watch them. So I'm put them all on 2. And that's window 2. We don't see window 1 because there's no waveform in it. So yeah, now this is nice because you can set this window up exactly how you want to look at them. And it takes you a minute longer to set things up because you have to go in here and set up all this stuff. But once you do it, it's pretty nice. Now, I want to show you another simulation. Here, let's go side by side. Okay. Now, here, let's get rid of this simulation. Let's do AC. Now, what we did is if you had a generator on the bench with an oscilloscope. Now let's do a Bode plot. Let's go to AC. Now see, I get my limits window again, but now it looks a little different because now we're dealing with frequency. So this is the start and stop frequency and the steps. And you can see the number of points, all that stuff up here. Input is the input, noise input is in, noise output is out 1. So all this kind of stuff is set up, and then you can come in here and look. We got, first thing you see is we're gonna have 2 graphs, graph 1 and graph 2, and X expression is F's for frequency instead of time. Y expression is the same as before, but now has a dB in front because now it's going to take the decibel. It's going to take the log of these things. And here's the range on the x-axis, and here's the y-axis. Now up here, it looks different, right? Because now it's in log, and we're going to have phase down here. And we have dB on the first 2 and phase on the bottom 2. So for graph 2. And then the log graph over here on the far left is chosen. So let's run that. And there you go. Now, since this one is highlighted right now, we can maximize it from right here and get a nice look at it. And then we can come down here, and if you look at these tabs, there's our schematic and there's our analysis. So you can switch between those. All right, so there's how you do your Bode plots. And you can see how you set them up. You play around with that. And all right, well, I hope that helped you learn how to get around a little bit more. Now, what if you wanted to print this? Go to File, Print Preview. And right now, it would just print this analysis. What if I want to print the schematic? Well, there it goes. I'm printing that too. Or I can hit this auto tile button. And I think that automatically tiles them when you print it, but you can hold your mouse button down and click on both of these things and get them in the same printout window together. Okay. Yeah, so now it's just going to print both these things into the same thing. So just wanted to show you how to print things too. All right, guys, hope that helped.
All right, so every time I show MicroCap, I try to throw in a couple extra little things. Some things are redundant, which hopefully helps kind of, help beat it in. And then I bring up some new things, just kind of throw in a little extra to help you learn the tool a little bit better. So let me know what you think of that, and hopefully this good practical knowledge, I think this is a good video and it's a simple circuit, R and C, voltage source, help you play with the tool a little bit, and it's practical. And yeah, and the transient that I showed you this time was different than the last one. So the last one was just using a probe. This one was setting up the transient window, and you can kind of see the difference in how they can work for you. So sometimes, a lot of times I use a probe one, and eventually if I playing with the circuit enough, then I'll go to the trouble to lay out that transient window, because if I'm going to keep on doing it, I'll end up spending more time setting up my windows after I do my probing than if I just take the time to do it to start with. But alright guys, hey, just a little more experience with MicroCap. Hopefully that's helping you out. And remember, voltage sources are not ideal. Just like all the other parts, you have to put a little bit of resistor in there to show that there is some impedance. Otherwise, that voltage source will give you all the current you want, and it'll make your simulations like not real. Alright guys, hey, thanks for patrons for all of your support. Thanks everybody for watching the channel. Thumbs up to the video, helps the video, the channel, so appreciate it, and we'll see you next time.